creativity units, which support student development from arts to entrepreneurship. By supporting the balance between knowledge and creativity, it will empower the maximum potential of the student. It is marked by the achievements that lead ITK to gain national and international recognition. ITK always believes that learning is no longer sitting in one place, but here and anywhere beyond collaborations. ITK supports Kampus Merdeka, a program initiated by the Ministry of Education, Culture, Research and Technology of Indonesia. Besides the student exchange programs, ITK has established certified internship programs with various corporate objectives, both state-owned and private companies. As a commitment to community service, ITK always has an aspiration to create innovation that could help the society to grow with technology advances. ITK will always continue to collaborate and build synergy with the government, industry, and higher education. By providing it all, it'll lead students to learn beyond the classroom, to foster global awareness and collaboration, so they could be more empowered and well-equipped to step towards the future. ITK is always committed to be more advanced and become the barometer of higher education in the Eastern Indonesia region. Starting from Kalimantan for the better Indonesia.
Welcome to Material and Metallurgical Engineering ITK. I'm Jatmoko Awali, the head of department. I know there must be a lot of questions about what we can do on this study program. Let me get you to take a look at the journey that you can choose to assess your universe. Our strategy to solve these various problems is by dividing our expertise in four broad research areas: material simulation and modeling, material manufacture, innovative material, material viral analysis. Let's find out what they are doing.
Material simulation and modeling expertise cover research for modeling and simulating important aspects in material science, including structure, properties, and behavior of materials. Basically, we are trying to construct models and identifying the correct approaches to test theoretical descriptions, experimental observations, or non-experimentable materials phenomena using various computer softwares.
Materials manufacturing studies the processing of materials to improve the efficiency and effectivity of product manufacturing. For example, casting, soldering, carburizing, welding, sintering, polymer extrusion, and composite curing.
Innovative materials focuses to improve materials by curating and developing innovative composite, metal, polymer, and ceramic, by expanding the design for devices and system of technological applications such as industrial, medical, and environment.
Material failure can lead to catastrophic accidents like the Titanic, airplane crashes, or collapsing bridges around the globe. The program teach the student to analyze cracks, corrosion, deformation, and many forms of material failure to find the causes and design the prevention of material failure.
So, that is a glimpse of the universe that you can choose. Let's start your journey with us to see more and know more. Because
There is no engineering without materials.
there is no engineering without materials.
Okay, ladies and gentlemen, welcome to the World Class Professor, bringing the theme Existing and Future Perspective of Electrochemical Sensors. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Respectable Director of Institut Teknologi Kalimantan, Professor Budi Santosa, PhD. Excellencies, the Vice Rector of Academic Affairs of ITK, Professor Nurul Widyastuti, PhD, and Non-Academic Affairs of ITK, Professor Dr. Muhammad Mashuri. Excellencies, the Head of Research and Community Service Center of ITK, Dr. Muhammad Purwanto. Honorable speakers, Professor Dr. Yasuaki Einaga from Keio University, Japan. How are you, Sensei?
Hi, good morning. Thank you very much.
Good morning. Thank you. And Professor Masato Tominaga from Saga University. Hello, Sensei.
Yes. Good morning, everybody.
Good morning. How are you?
Fine.
Thank you so much. And the last Associate Professor, Dr. Zaini Haryati, Modzan University, Mara, Malaysia. Hello, Dr. Zaini.
Good morning.
Waalaikumsalam. How have you been?
Great, thank you.
Thank you so much. All of the invited guests from the officials of Institut Teknologi Kalimantan, lecturers, researchers, colleagues, and students from various institutions. Ladies and gentlemen, my name is Gusti Umindia, and of course, it is my pleasure to be a master of ceremony in a beautiful day. Now, behalf on the World Class Professor Committee who organized this event perfectly, I would like to extend a very warm welcome to all of you. We appreciate you taking the time of your busy schedule to join us today. I will deliver the rundown for today. First, opening session, and then second, singing the national anthem of Indonesia, Indonesia Raya, and singing the March of ITK. And then we, together, there is a performance, Dayak Contemporary Dancing, and then event reporting from the chairman of the World Class Professor, Dr. Eng Yunita Triana, following by opening speech from Vice Rector of ITK, Professor Nurul Widyastuti, PhD. And then speech and discussion session, leading by a moderator. And then signing MOU ceremony between Integrated Laboratory of ITK and the Diamond Electrochemistry Laboratory, Keio University. And closing. Before we continue to the main agenda, let us singing and listen together the national anthem of Indonesia, Indonesia Raya, following by March ITK.
Indonesia,
Thank you for your respect and kind attention. Next, a special performance from our students, Dayak Contemporary Dance. Please enjoy the show. Thank you so much. That's a wonderful dancing performance from our student. So the next fifth agenda for today is event reporting from the chairman of the world-class professor, Dr. Eng Yunita Triana. She is a lecturer in Materials and Metallurgical Engineering Department at ITK And she has graduated from KU University in 2022 under Professor Einaga Yaswaki supervision and successfully granted the world-class professor in the same year. Dr. Yunita, the screen and time are yours.
Okay, do you hear my voice? Hello, Lala Sensei.
Yes, sure.
Okay.
Very clear.
Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Your Honorable Director of ITK, Professor Budi Santosa, PhD, the Vice Rector of ITK, Professor Nurul Widyastuti, PhD, the Head of Research and Community Service of ITK, Dr. Muhammad Purwanto, the Head of Earth and Environmental Science, Mrs. Umi Soliha, Head of Material and Metallurgical Engineering, Mr. Jatmoko Awali, Head of International Office, Dr. Musyarofa, and keynote speaker, Professor Dr. Yasuke Inaga. Good morning, Sensei. Invited speaker, Professor Tominaga. Good morning, Sensei. And Associate Professor, Dr. Zaini Haryati. Assalamualaikum. The Committee of World Class Professor Third Series and all the audiences today. I am Yunita Triana. I am the chairman of the World Class Professor Program. And today, guest lecture program with the topic Existing and Future Perspective of Electrochemical Sensors. After the implementation of the program, World Class Professor first about workshop program and the second series about the international webinar, today we will have the final World Class Professor third series, and today's program is a guest lecture. The topic today is discussion regarding the existence and potential of electrochemical sensors for many applications such as industrial and then environmental and also medical fields. And this is the final series of knowledge about the carbon-based electrode technology to implement it to the sensors. In addition, ITK requires cooperation to support collaborative research with top university in the world to grow up rapidly. We already have MOU, Memorandum of Understanding, with Saga University. Thank you for Tominaga Sensei. And also we have MOU with University of Mara, University Shah Alam. Thank you for Dr. Zaini Haryati today. And next step is starting collaboration with KU University. Special event today is signing legal collaboration with ITK and KU University between the laboratories. Thank you for Professor Yasuke Inaga, who support me always along my PhD program. And today also he support me to have legal signing collaboration with ITK. Finally, thank you so very much for all your attention, for all your enthusiasm to this event. I hope that all of you can enjoy the event well. And once again, thank you very much for your support. I take back the time to Lala Sensei.
Okay, thank you, Dr. Yunita. And now, to formally kick off our event, it's my pleasure to invite the Vice Rector of ITK, Professor Nurul Widyastuti, PhD, to deliver a remark. Please welcome Professor Dr. Nurul Widyastuti.
Thank you very much, moderators. Very good morning, everyone. Assalamualaikum warahmatullahi wabarakatuh. Honorable Speaker, Professor Yasuaki Einaga from Keto University, Professor Masato Tominaga from Saga University, Associate Professor Dr. Zaini Haryati from UITM Malaysia, and Head of Research and Community Service, Institut Teknologi Kalimantan, Dr. Muhammad Purwanto, and also Dr. Yunita Triana as a host for this event, distinguished academic member of Institut Teknologi Kalimantan. It gives me great pleasure to welcome you all in the world-class professor meeting series that today bring up the themes on existing and future perspective of electrochemical sensors. Today we will have an agenda on the agreement of Institut Teknologi Kalimantan and KU University. With regard to the topic of electrochemical sensors, research and development of electrochemical sensors allow the study of the new materials, the application of samples of different natures, new manufacturing methods, and strategies to enhance the selectivity and detection limit. Based on the material behavior at the nanometric scales, promising new possibilities arose in the area of research and applications of electrochemical sensors. As we know in our daily life, some example of the applications of electrochemical sensors are environmental monitoring, health and instrumentation sensors, and sensors related to machines such as automobiles, airplanes, mobile phones, and technology media. The challenge now and in the future are finding smaller sensors with more sensitivity and more selectivity, and with lower productions and maintenance costs as well. Since I have background in chemistry, I believe the research in sensor will contribute to all of the focused research in the Institut Teknologi Kalimantan, which are energy, smart city, marine, as well as food and agriculture research. To accelerate this, collaboration is the key. We do hope that by discussing the topic, we will get insight, new idea, initiative, and develop collaborations between us in order to increase the quality of education, research, human resources, and facilities. Our collaboration between Institut Teknologi Kalimantan and other universities, especially today we have collaboration with KU University, will always bring us benefit for both sides in order to increase the quality of education and research. We welcome you all for collaborations and develop activities together. Finally, Bismillahirrahmanirrahim, I open the world-class professor meeting series with the themes on existing and future perspective of electrochemical sensors. Hope all of you enjoy the meetings and have benefit from it. And thank you very much. Assalamualaikum warahmatullahi wabarakatuh. I give back to moderator.
Okay, thank you so much for the opening speech, Ibu Nurul Widyastuti. But before we continue, please we do a photo session. So please everyone here use a virtual background and open your camera. The operator or the committee will lead the photo session. Please give me the sign. The committee, please.
Okay. I will taking some pictures of the attendance in this room. Make sure your camera has turned on. I will taking pictures from the first page. 1, 2, 3. Okay, and now the second page. 1, 2, 3. Okay, the third page. 1, 2, 3. And the last fourth page. 1, 2, 3. Thank you.
Thank you so much. Thank you so much for all of you for giving your best smile for the photo. And then, without further ado, I will invite the moderator of today who will lead the speech and discussion session. He is Dr. Andi Idil Ismail, or commonly known as Pak Andi. He is one of the lecturers in Mechanical Engineering Department, Institut Teknologi Kalimantan, who has finished his doctoral degree at Swiss Federal Institute of Technology, Lausanne, Switzerland, with research interest in metal alloy, especially in titanium, steel, and high temperature materials, and also interest in materials characterization. Now he is taking responsibility as a head of mechanical engineering undergraduate program in Institut Teknologi Kalimantan. So please welcome Pak Andi, time is yours.
Thank you very much for the brief introduction. Hello everyone, it's nice to meet you, especially to our eminent and prominent speaker, especially Professor Tominaga and Professor Zaini Haryati and Professor Einaga from KU University. I will be chairing the talk session today. Today we have three eminent and prominent speaker from KU University and Saga University and University of Teknologi Mara, Malaysia. The first speaker will be delivered by Professor Einaga, but before that, I will briefly introduce you about Professor Einaga. Professor Einaga obtained his bachelor degree in chemistry from Tokyo University, and then he continued his master's degree in the same department, also from the University of Tokyo, and then he obtained his PhD degree from Department of Applied Chemistry in the same university at the University of Tokyo. Currently, he is holding a professor position in Department Chemistry at KU University. His interest is functionally material science, electric chemistry, photochemistry, and diamond electrochemistry. He has published more than 100 publications in a peer-reviewed journal and publication conference. So today, Professor Einaga will deliver talk about dopamine detection, glucose detection, and influenza virus detection. Professor Einaga, your time is yours. You will be talk about 30 minutes, around 25 minutes for the talk, and continue with 5 minutes question and answer.
Okay, thank you very much for a very nice introduction. Okay. Okay, thank you again. Selamat pagi. Good morning, everyone. My name is Yasaki Einaga from Keio University, Japan. So, first of all, I want to say thank you again to Nita-san for giving me many chances to talk here. So actually, this is a third time in this program. So I'm very happy. But some of you are tired of listening my talk, I guess. So actually, last time I talked about the background of bond of diamond electrode carefully, not only by myself, but also by other experts on diamond electrochemistry. So today, I'd like to. Today's topic is focusing on the sensor application, electrochemical sensor application. So today I want to talk about the sensor application using bond of diamond electrode. Okay, so but anyway, before that, I must introduce very briefly again about the background of bond of diamond electrode. Okay, so I'll start now. So I told last time I talked about the diamond electrode last time, but just briefly I'll introduce again. Okay, so diamond is insulator, as you know, but the important point is to dope boron. So when the boron is doped in the very low concentration, the conductivity increases. This is a boron concentration like this. So when the boron concentration is low, this shows a p-type semiconductor. Okay, this insulating diamond and semiconducting diamond are studied by many people. So these studies are very popular. However, we are focusing on this highly boron doped diamond. So 0.1% or 1% boron is containing in this diamond. So this diamond shows a metal-like conductivity, shows a like conductive material. So we are using this one as electrode material. This is our research. So the preparation of boron doped diamond is also explained last time in detail. So just I want to show it briefly. But we are using a microwave plasma CVD system. By using this microwave plasma, then as a carbon source, we are using acetone. This is a carbon source, and by using thorimethoxyboron is also the boron source. We can control the concentration and we can control the conductivity of the diamond. Okay, so we are making a highly boron doped diamond by using this system, and this is a polycrystalline boron doped diamond. Okay, so by using this boron doped diamond electrode, so far in these 20 years, we applied this diamond electrode to many fields. So actually today's topic is a sensor, so the electrochemical sensor is one of the main application. So we focusing on this application for a long time. And then recently, in this 10 years, we expanded the application, not only sensors, but also CO2 reduction or wastewater treatment or electrochemical organic synthesis or electrochemiluminescence or ozone water generation. Anyway, so many applications are possible by using boron doped diamond. So these applications are also interesting. And last time, carbon dioxide reduction also introduced. But anyway, sorry. So again, also not only application, but also this fundamental study is also very important. Anyway, today I'm focusing on this one. Again, so last time also I showed some of the example, but today I want to show some example in more detail. Okay. So before coming to the application, I will briefly show the advantage of boron doped diamond electrode again. Maybe this is also explained last time. So the one important point is a wide potential window compared to the other electrode. Other electrode shows the oxygen evolution and the hydrogen evolution is observed around here, oxidation, oxygen evolution, around here, hydrogen evolution, but no reaction, no hydrogen evolution, no oxygen evolution shows the potential window. But the potential window is always like this. But in boron doped diamond case, potential window is very wide. Oxygen evolution is difficult. Hydrogen evolution is difficult. And also the low background current is very good point for the sensor, electrochemical sensor application. In this region, inside the potential window, no background current is very, very small. So it means the signal to background show is very high. So it shows a very sensitive one. So this is the advantage. I explained again. Okay, anyway. So by using this mainly two important properties, so far we reported many electrochemical analysis, electrochemical sensor application. For example, for environmental sensor like this, and not only that, but medical application. Recently, Dr. Nita-san reported the oxygen detection in blood, also reported in recently. Okay, so today I want to because if I introduce all of the example, of course, time is not enough. So today I will focus on this 3-4 topics. Okay. Okay. So firstly, I will introduce the free chlorine sensor application, and then arsenic sensor and the in vivo detection of dopamine and the influenza virus also will be introduced later. Okay, so the first example is a chlorine sensor. Actually, last time also this sensor is introduced very briefly, but today I will show in detail more about this chlorine sensor. Okay, so this is one of the recent example for the industrial application. That's why I want to introduce this example. So free chlorine is important to disinfect. So this is a hypochloric acid or hypochloric acid. Okay. Okay, this free chlorine detection, the purpose is, for example, to detect chlorine in free chlorine in tap water or swimming pool. And not only that, but some food factory or hospital also need the detection in this concentration region. Anyway, so to detect chlorine, so far the DPD method is normal. DPD is this chemical method is normal. So when we want to measure chlorine, this DPD reagent should put in the sample, then show color and detect the absorption spectra. Okay, so this is a bit troublesome because we need these chemicals, but so without chemicals and very simple method. This is the electrochemical method. Okay, so this is our purpose. Actually, 2008, a very long time ago, we reported the first example showing the detection of free chlorine. So as you can see, when the conventional electrode, glassy carbon, platinum, and gold is used, the oxygen evolution is observed at around 1.2 or 3 volts. So the detection of chlorine oxidation is very difficult, overlapped here. On the other hand, when our diamond electrode is used, the clear oxidation peak is observed and no oxygen evolution observed. So it means this signal is reflects the concentration of chlorine directly, and the sensitivity is very high. So this is due to the advantage of bond of diamond, of wide potential window, and also not low background current. Okay. So then we could observe the calibration curve depending on the concentration. As you can see, in this region, or not only this region, but also very low concentration region. For example, the tap water analysis is possible in this very low concentration, is also possible to detect. Okay, so this is the advantage of diamond electrode. Okay, so actually, we have reported this result in 2008, long time ago. Then this result was sleeping for a long time. Okay, so and then recently the situation is changed. The importance of chlorine sensor is increasing. Okay, so why? Because the Japanese government set up this HACCP is one of the rule by this is set up by Japanese government to keep international standard for food sanitation. So this is actually to set up for Tokyo Olympic game last year, actually, the government decided. Anyway, so for this purpose, there are many companies that try to detect, should monitor the chlorine concentration. To monitor concentration has become more important. Okay, so then we started several years ago, 3, 4, 5 years ago, we collaborate with a company to try to produce this chlorine sensor based on our technique. Okay. However, in order to realize the application, the actual sensor, we encounter some problem. So before that, we should study the fundamental again more carefully. Okay, firstly, when we started the collaboration, firstly, we try to understand the mechanism more in detail. So by using this Cottrell plot, and then we could know the electron number for the reaction. By this Cottrell reaction, the oxidation reaction is contains 1 electron oxidation. So it means this ClO minus oxidized in this 1 electron reaction. So this is confirmed. And then we encounter the problem. What is the problem? This is pH, you know. So 2008, we reported the oxidation peak is very good, but this oxidation peak shows the pH dependence like this. When the solution is acid, the peak disappears. When the solution is base, the peak increase. So if the pH of the solution changes, the signal is changing. So this is a problem for the actual sensor. However, as we know, this is obvious. In 2008, we didn't care about the pH so much, but actually this is normal. This HClO and ClO minus shows this kind of equilibrium, and the pKa equal 7.5. So when the pH is high, the ClO minus is almost 100%. On the other hand, when the pH is low, HClO is dominant. So this is obvious. So our result shows the oxidation of ClO minus oxidation. So it means this is reasonable, of course. When the ClO minus is much, of course the signal is high. When ClO minus is low, signal is low. This is reasonable. However, what we want to know for the actual sensor, practical sensor, we need to know the concentration of both free chlorine, means both chlorine like HClO plus ClO minus. So this is not enough. Only this one is not enough. So then we try to study the reduction also. Okay. So in this case, we focus on the reduction reaction also. As you can see, reduction peak also shows a pH dependence. When the pH is low, the reduction peak appear, and the pH is high, reduction peak disappear. So this reaction also shows almost 1 electron reaction. So we confirmed this reduction reaction is confirmed to this HClO reduction. Okay, so this is the result of both oxidation and reduction. As you can see, for application, the measurement of both oxidation and reduction is important. In case of oxidation, this shows the ClO minus oxidation, and this reduction shows the HClO reduction. So then it shows the pH dependence like this. This is reasonable. So we confirmed the total should be the total of this current. This current and this current total show the free chlorine concentration like this. This is a reduction current, and this is oxidation current. This is a total. As you can see, it is independent of pH. In any pH, we can know the concentration of free chlorine. Okay, this is a new discovery after the careful study. Okay, so this is actually advantage of boron-doped diamond of wide potential window. So other electrode cannot detect both oxidation and reduction. So only wide potential window diamond electrode can detect both. This is also shows the advantage of diamond. Okay. So this is one of the important discovery. And another important point is to realize the practical application. This is a reproducibility. This is also very important fundamentals. The initializing electrode, it means the reproducibility is very, very important for applications. However, we know the surface is very important to show the current. Okay, so as grown, after the plasma preparation, the boron-doped diamond shows the hydrogen termination like this. However, the surface can be oxidized like this. We call this surface is oxygen termination. So this hydrogen termination and oxygen termination is very easy to control, but in other words, this shows the sensitivity is also different. So we should control the surface very, very carefully. For example, if some surface is different, the signal of the current will be different. This is a problem for the application. Okay, so in this case, of course, this hydrophilicity, hydrophobic. This is hydrophilic. This kind of property also different, but not only this property, but electrochemical property is important for the application. Okay, so we should initialize the surface, for example, to hydrogen termination. This is important. So anyway, we know by cathodic reduction reaction to show the hydrogen generation, the surface can be hydrogen termination. We know this phenomena so far also, but of course everybody knows by cathodic reduction, this surface can be converted to hydrogen termination. But this condition is not unified like this. So depending on the report, the condition is different. Someone says -3 volts 30 minutes. Someone says -10 milliampere 10 seconds is enough to show it. But this is not confirmed yet. So then we very, very carefully to study this hydrogenation. It means cathodic reduction. In which condition this initializing is very enough. So then we try to perform the cathodic reduction by using the various pH. For example, in acid solution and -3 volt. In basic solution, -3 volt. What happened on the surface? This is checking by ferroferi-cyanide redox couple, electron transfer rate is studied. I mean, this small peak separation shows the hydrogen termination. This large peak separation shows the oxygen termination. So we can estimate. Estimate is how much amount of hydrogen, how much amount of oxygen is shown. Anyway, by using, for example, by using acid solution and cathodic reduction, then this shows very small peak separation, means this shows the completely hydrogen termination. However, when the solution is low, pH high, in that case, the termination becomes still oxygen. So this acid solution is important to initialize the surface. The proton is important. Low pH should be active. Active means hydrogen termination. So to confirm this termination, we also study the XPS spectra. XPS spectra also supported in case of acid solution. The CH is too much like this. Okay. And not only this experimental result, but also we collaborate with Tateyama Sensei, Dr. Tateyama, in he's an expert of the theoretical scientist. So he calculated this the surface reaction by using the DFT calculation, and our conclusion is after the cathodic reduction, in the beginning at high negative potential, the proton is reduced to the atomic hydrogen radical. It is atomic hydrogen, and then in this case the proton and OH termination react. Then by reduction, this water molecule is removed. Then the dangling bond is generated. Then atomic hydrogen is react with this carbon, then become hydrogen termination. This kind of mechanism is also confirmed, not only by experiment, but also this theoretical calculation. Okay. So another important fundamental is in situ surface analysis. So by we want to confirm the surface very carefully to know what happened on the surface, and then we prepare the bond of diamond on the silicon prism. Then we could finally monitor the surface directly in situ during the electrolysis. So then by using this technique, we could confirm the surface termination directly during the applied potential, like this 0.5 volt to 3 volt. As you can see, the COH bond is generated. So it means the surface oxidation is directly confirmed. Okay, anyway, based on these fundamental study, and we collaborate with the company, then finally we prepare the prototype. Then prototype is produced by this collaborating company. Then finally, very recently, this diamond sensor, free chlorine sensor, is commercially available now. So I'm very happy. So because, but it takes a long time to be this one. Okay. So maybe I have more 5 minutes, okay? Sorry. So I should finish in 5 minutes. So I must skip some of the other example. Okay, so I wanted to show another example of showing the arsenic sensor, but time is not enough, so I must skip this arsenic sensor. And also I wanted to show the dopamine detection. I will very briefly about this dopamine detection. Okay, by using this micro electrode. This is also, we are recently focusing on the micro electrode. This size is very small like this, and by using this one, we can detect something in vivo. Okay. So this is a preparation. On this tungsten wire, the bond of diamond is deposited. So in 2007, this is a long time ago, but this is the first, just I want to introduce this result of the detection of dopamine. You know, dopamine is a neurotransmitter in brain. You know, for example, when you are hungry, and when you are hungry and when you find some food, the dopamine released in the brain. So not only that, but some anyway, the reward or some present, some such kind of activity, the dopamine is important. However, the ascorbic acid can interfere. So ascorbic acid, the vitamin C, you know, ascorbic acid also exists in brain. So this can interfere. This is a problem. But by using bond of diamond, we can control the surface. As I mentioned before, the hydrogen termination can be converted to oxygen termination. In this hydrogen termination, the dopamine and ascorbic acid shows the same potential. However, when the oxygen termination shows the peak are different like this, dopamine and ascorbic acid shows the different oxidation peak. So why? Because the ascorbic acid shows the negatively charged one and the oxygen termination shows a negatively charged one. So this is electrostatic repulsion can shift the oxidation potential of ascorbic acid. So we can separate these two peaks. So we can detect dopamine in brain. Then we collaborate with the medical school. Then we inserted our bond of diamond microelectrode in the brain of the mouse. Then applied electric stimulation. By electric stimulation, the dopamine released. So this is a amperometric measurement applies a constant potential, and here the electric stimulation, dopamine release, dopamine release, dopamine release. This kind of signal is observed very clearly. So this is in vivo detection. And the important point is reaction kinetics. So when we use the carbon fiber electrode, this is a comparison with the bond of diamond. This is not in vivo. This is a flow cell experiment. As you can see, when the here dopamine released, here dopamine is introduced, the current increase. And here, when dopamine stops, the current is recovering. But time is a little bit delayed. On the other hand, when our bond of diamond microelectrode is used, as you can see that when the dopamine is introduced, the current increased here like this. And here dopamine stops, and this is recovered. So it means the quick response means we can measure we can apply to the real-time measurement. This is an interesting example of the real-time measurement of dopamine release. As you can see, this is a food. This is a mouse, and we monitored the dopamine in this brain, both. As I told you, when we are hungry and we find food, the dopamine release. When dopamine release, this is the experiment. As you can see, when we open the door, this mouse only shows the food. So this is the result. As you can see, when this red one means with food, only after opening, after 0.5 seconds after opening the door, the dopamine release is observed. So it means just after 0.5 seconds, dopamine release. This kind of timing mechanism, including the timing of the dopamine release, can be studied by diamond electrode. This is very important. So real-time measurement is very possible by using diamond. I'm sorry, time is...
Yes, sorry, Professor Inagaya.
Okay, time is over. So I want to show the another example, but this is also report introduced last time, so I must also skip. Okay, this is also I showed last time. Okay, just 1 minute, please.
Okay, go on. No
1
problem.
minute, please. Just I want to show the important application is the influenza virus detection. Recently, the coronavirus is also important, but a long time ago we reported the influenza virus detection. So how to detect influenza virus? This is the influenza virus. So we modified the special functional molecule on this surface. This is a hemagglutinin binding peptide is designed, and this peptide can catch influenza virus. So this peptide is modified directly on the surface of bond diamond. This is our technique. Actually, by electrochemically modified, then here we designed this azide terminated peptide. So by using this click reaction, you know, azide and alkene. So actually, yesterday, last night, Nobel Prize of Chemistry was related to this click reaction. So that's why I wanted to introduce. Anyway, we also use this click reaction. Then we could modify the surface of peptide. And by using this peptide, we can catch the influenza virus. Then I must skip the detail, but anyway, by using this modified diamond electrode, very sensitive influenza virus detection was possible. So now we are also making the similar coronavirus detection system recently. Okay, I'm very sorry. So actually, our bond of diamond can apply to the many fields, not only sensor but also other field. But anyway, for sensor also we can apply to the many fields. Okay, I'm sorry, time is over. Finally, I want to say thank you to all the collaborators. Okay, thank you very much for your kind attention.
Thank you very much, Professor Einaga. This is a very interesting topic, especially for the current situation. Now I will open probably 1 or 2 questions to the floor or to the participants who want to discuss the research from Professor Einaga. Please raise your hand and okay, 1. Please go on. 2. Okay, please.
My voice is loud and clear, sir.
Yes. You can go.
Okay, thank you for the opportunity. Thank you, Professor, for the lecture that I can say. So my question is, let me introduce myself before. My name is Yogi Mirza from Mathematical Engineering for Kalimantan Institut Teknologi. I have two questions. The first question is on the chlorine sensor during its application in the field, such as swimming pool. Are the depth of the sensor using can be affecting on the result? So in the surface and in the bottom of the swimming pool, is there any difference for the result of measurement? And the second question is about the PDD sensor.
Sorry, I couldn't catch the first question. So regarding the chlorine sensor in swimming pool, so
probably the question is this sensor detection limit similar with between the surface and the bottom in the swimming pool?
Detection limit in sense bottom and top.
Yes.
In swimming pool.
Yeah. Is it similar and or different?
In swimming pool, bottom and top, the concentration, what's the difference? This is the question. Okay. This is, I think this is in solution in swimming pool. This concentration will be homogeneous, I think. So the concentration is not so different, I think, because if some particle or such kind of one can be precipitation, but in ion or just dissolved one is very homogeneous in solution. It's my opinion, but I'm not sure. Okay, I'm sorry. Interrupt your second question.
Second question.
Okay, for the second question, the last lecture about influenza virus detection. Is there and is application want to be detecting coronavirus too, and what kind of difficulty you're facing for the influenza and coronavirus in the different, because maybe it's same but it's kind of different. What is maybe that what is hurting?
Okay, this is a good point. So yeah, actually the most important point is this one. In this case, this influenza virus have hemagglutinin protein here. So this, we designed this one. This one is a hemagglutinin binding peptide. This is an important point. For example, if this is a coronavirus, so we should make something to catch coronavirus. So it means, for example, recently we are making the antibody of the coronavirus. This is well known. So everybody now, when we go to some hospital and we test some antibody test, so this antibody should be modified on the bond of diamond. This is the strategy. So of course, this antibody, not only antibody, this peptide also possible. Anyway, such a interaction is strong. This is okay. But our technique, our important technique is to modify the surface like this, electrochemical modification, and by using quick reaction. This is important. Okay, so yes, you are right. That part is the more important. Okay.
Okay, thank you, Professor, for the answer. Maybe that's my question. Thank you very much.
Thank you very much for your question.
Okay, thank you very much. I think we have no more time. So those who want to post question, I think can every time contact Professor Einaga through email or any contact direction to them. So for this, we conclude the session for Professor Einaga. Let's give a round big applause for Professor Einaga.
Thank you very much.
Thank you very much. So now we move to the second speaker, which will be Professor Masato Tominaga. Professor Masato Tominaga will talk about phosphate ion sensor and skin gas sensor. But before that, I will briefly introduce you about Professor Tominaga. So Professor Tominaga is currently holding a professor position at Graduate School of Science and Engineering at Saga University. And he is also now holding adjunct professor position since October 2021 at Institut Teknologi 10 November Surabaya. Professor Tominaga is obtained his bachelor degree and master's and doctoral degree at the same university at Kumamoto University. So Professor Tominaga research field is electrochemistry, bioelectrochemistry, surface chemistry, environmental chemistry, as well as nanocarbon chemistry. He has secured many research funding from many organizations, and also has published more than hundreds publications in the last 5 years. So Professor Tominaga, the time is yours.
Okay, thank you very much for your kind introduction. My voice is clear. Can you listen my voice?
Yes, your voice
Yes,
is
I can
clear.
hear. I can hear.
Okay, thank you very much.
Quite clear.
I will share my slide. Can you see my slide? It's okay?
Yes, it's quite clear.
Okay, thank you. Selamat pagi, everybody. Nama saya Masato Tominaga Universitas Saga. So first of all, I would like to say thank you very much to Unita Sensei, Dr. Unita Sensei, and also Gusti Sensei, and also academic organizer for this seminar. I'm very honored to be here as a presenter of this seminar. So today's my topic is phosphate ion sensor and skin gas sensor by using electrochemical technique. So at first, I would like to introduce my research topic briefly. So there are four main research. One of them is bioelectrochemistry. We use the enzyme and the protein for develop enzyme sensor and enzyme catalyst biofuel cell. And then also we are developing a microbial fuel cell. Now we are investigating MFC to make an electronic generation in the body field. And then we use the nanomaterial for using a catalyst or a sensor. And then I also developing a tantal capacitor, tantal condenser. This one is collaborated with Panasonic. So if you are interested in my research, so please join to my homepage. So also in Bahasa Indonesia. Okay, today's my topic is this one and this one. Okay, Japanese government developing a Society 5. So that is the Pramano DX. So the many sensor is located in the many field. This is sensor. So the sensor is located set in the many field, and then collect the data, and then send to the AI analysis and feedback to the each person. That is Society 5. So in this system, the sensor is very important. So physical sensor is developed well. On the other hand, chemical sensor is not much developed. Maybe only gas sensor. Okay, so what kind of sensor is useful? There are some sensor. I think the most popular sensor is metal oxide semiconductor to detect the gas. Maybe in your home, you set up the metal oxide gas sensor to detect the methane gas. So I would like to talk about the electrochemical sensor. So metal oxide sensor is, cost is cheap, but selectivity is lower, poor. On the other hand, electrochemical sensor is very nice selectivity. That cost is a little bit higher than metal oxide gas sensor. But I think, in the future, the people use the electrochemical sensor, that this cost is close to the metal oxide sensor cost. So anyway, so today's my talk is phosphate ion sensor by using a cobalt oxide nanoparticle modified electrode and the skin gas sensor, ethanol gas sensor, by using a cellulose nanofiber platform electrode modified with enzyme. So the first topic is phosphate ion sensor. This research is achieved by my student, Miss Shaima Linda Sari. Now he is a doctor, third grade, who graduated from ITK. Okay, so for fertilizer is including many phosphate. Phosphate is, because phosphate is an essential element for the plant. On the other hand, too much phosphate released to the sea or river, the surface of river and the lake is changed to green because of too much plants in the river and the lake. So the monitoring of phosphate ion is very important to keep the environment. The suitable concentration of phosphate is like this. It's reported by like this research paper. This is very low concentration. Of course, we can detect such a small, very low concentration of phosphate by using a spectroscopic method. So by using fluorescence, we can detect the like this very low concentration of phosphate ion. But this spectroscopy method is not useful for monitoring every day, every hour. On the other hand, electrochemical method is very convenient to detect the phosphate. But the sensitivity is not enough to detect a low concentration of phosphate. So my target is development of very sensitive, very high sensitive detection of phosphate ion. So cobalt is, so this is cobalt-based phosphate sensor, right? Cobalt. Cobalt, this metal is very useful to detect the phosphate ion. So I synthesize cobalt nanoparticles. Okay, so I would like to show you. I would like to introduce briefly this method. Okay, I use multi-wall carbon nanotube. This one. This surface is modified with PBI. PBI is a polymer, polybenzimidazole, like this polymer. The surface is covered with PBI because the PBI can disperse the multi-wall carbon nanotube well. Also, this PBI can be fixed the cobalt nanoparticles. Okay, so after that, I synthesize cobalt nanoparticle on the multi-wall carbon nanotube surface by using like this method. Okay, this is a TM analysis. You can see multi-wall carbon nanotube here. And then at the surface, you can see cobalt nanoparticles here and here. These nanoparticles are very uniform, and the size is also controlled from 4 to 5 nanometer. And also the surface crystal is usually 2 to 0 of CO3 or 4. This is more again, this is a TEM image. You can see a multiple carbon nanotube here, and this is the cobalt oxide nanoparticles. And this one is a PBI, this polymer. This is a result of XRD and XPS. From the XRD result, we can say, I can say that these cobalt oxide nanoparticle is mainly CO3O4 and a minor amount of COO. The mainly CO3O4. And then from the XPS result, I can say the cobalt oxide, cobalt nanoparticle is fixed to the this material, this polymer, because I can see CON bond here in the N1S peak. Also, in the CO2P peak, we can observe CON binding peak here. Okay, I move to the electrochemical method. I use the cyclic voltammetry and open circuit potential. So this is cyclic voltammetry of when I use the cobalt oxide nanoparticle modified electrode. Okay, so when there is no phosphate ion, I cannot detect any redox reaction of phosphate like this one. And then if in the presence of a phosphate ion in the solution, I can observe like this peak due to phosphate ion. And then if we use the cobalt wire, so what's happened? Okay, so when we use cobalt wire, so the behavior, redox behavior is little bit complex compared to the cobalt nanoparticles. Because cobalt wire is polycrystalline surface, right? So it means that there are many kind of surface, crystal surface. So the surface, this phosphate detection is depend on the surface reaction. So surface is different, so it means the reaction is a little bit different. The potential is a little different. So it makes complex to detect the phosphate ion. But when we use the cobalt nanoparticles, so this surface is almost 2,2,0 surface. So the surface is very controlled, limited. So this reaction is very limited. Only 2,2,1, 2,2,0 surface reaction. It's very simple. Or it means we can make a high sensitivity phosphate ion sensor. Okay, this is the phosphate ion detection by using potentiometry. So this is background potential. When we add this very small amounts of phosphate ion, the potential changes to here. And then again, I add the phosphate ion, the potential is changed here. Like this behavior is observed in pH 4 and pH 7. Okay, this detection range is enough to detect the suitable concentration of phosphate ion. Also, I check the ICP method to check the phosphate ion concentration. So the creek and the water, the pH 4 and 7. So in the ICP result, we observed like this concentration. This is our sensors result. This result is similar to ICP result. So it means my sensor is can detect the phosphate ion. Okay, this is as a conclusion, we developed the very high sensitivity phosphate ion. So this previously electrochemical sensor to detect phosphate ion is not high sensitivity, but when I use a cobalt nanoparticles modified electrode, and I achieved very high sensitivity, high sensitive phosphate ion sensor. This result, this achievement is already published in the, this journal, and they are selected as the backside cover. Okay, next topic is skin gas sensor, the ethanol. This research is done by my student, Ms. Chitra, who graduated from ITS, Surabaya. Okay, I think you know mobile type glucose sensor. This is very famous. This market is so huge. Also, this sensor uses the disposable electrode chip, maybe like this one. And then this sensor uses an enzyme to detect glucose. Mechanism is like this one. Okay. And this enzyme oxidizes glucose. Glucose becomes the gluconolactone. After this reaction, this enzyme is changed to reduced form. And then this reduced enzyme reacts with the, some another complex. And then this complex reacts with the electrode. As a result, we can observe the oxidation current. So when glucose concentration is high, we can observe the high value of oxidation current. This is a mechanism, principle of glucose sensor. Okay, so today I focus on the skin gas. So skin gas is containing many type of organic gas. So VOC, acetone, ethanol, aldehyde, methane, ammonia. And then these gases are related to the disease and our body condition. So to detect these VOC is, when we detect it like this, VOC, we can check our body condition. For example, acetone gas is related to the, like this disease, but a concentration is very, very low. So the sensor sensitivity is required ppb level, not ppm, okay? So when we developed the skin gas, the high sensitivity, also specific detection are required because skin gas is mixed gas of these VOC. Okay, so of course, when we use very nice equipment, we can detect skin gas, such as GCMS, like something like that. So this machine can detect very low concentration of skin gas, VOC. But the mobility is no good. I would like to develop the, like this device. Okay. So wearable is required. So maybe the solution is thin film device. And then I want to sensor every day. It means disposable and low cost electrode. Why? So VOC is strongly depends on the body condition. Our body condition is changed every day, right? So I hope in your future, so you wear the smartwatch, and then the sensor is set in the smartwatch in here, and then we can check our body condition every day. I want to make like a system. So what material is suitable for making the disposable electrode? I selected the cellulose nanofiber because a CNF is biodegradable and also low cost. Also high flexibility, yes. I prepared the CNF seed and I prepared the 3 electrode system on the CNF seed. So at first, this is the preparation of electrode. At first, I prepared the CNF seed like this one. We can prepare easily like this seed. And then we cast a multi-wall carbon nanotube on the CNFC seed. As a result, we obtained like this CNF seed electrode. And then I set the CNF electrode like this one, and then this electrode system is used for the gas detection. This is a SEM image of the surface of a CNF seed. This is surface and cross section of a multi-wall carbon nanotube layer. You can see many space in the multi-wall carbon nanotube surface layer. So it means the gas is easily diffused in the inside of electrode surface, electrode layer. It makes high sensitivity detection. Okay, I use 2 types of alcohol enzyme, alcohol dehydrogenase enzyme. Okay, PQQ-ADH and ADH. But this ADH from yeast, I could not detect any redox catalytic reaction. But when we use a PQQ-ADH, we observed very nice catalytic oxidation current based on directly electron transfer reaction of enzyme with electrode, like this reaction. So mechanism is like this one. So enzyme adsorbed on the electrode surface, and this enzyme is oxidized form, and then this enzyme reacts with ethanol, and then this enzyme changes to reduced form, and then this reduced enzyme give electron to the electrode. We can observe the this reaction as a current, and then this enzyme return to the initial stage, and then like this cycle is continuing. And this is a result. At first, we use ethanol gas tissue paper containing an ethanol solution. So this is the catalytic oxidation current. This peak current, this catalytic current value is depend on the ethanol concentration. It means we can use this electrode to detect ethanol to evaluate the ethanol concentration. Okay. Also, we may prepare the calibration curve by using a GC like this one. And then, so this is amperometric result. So when we use very small, low concentration of ethanol, we can detect like this one. No. And then this is the detect observed current versus ethanol gas concentration, the ppb. In our system, I can detect 55 ppb of ethanol gas by using my electrode. This is a result of real detection. And this person is me. So this is our electrode system. No, this system set on my hand here, and then I drank Japanese sake. Okay, this alcohol is 50%. I drank a very little of alcohol, around 20 milliliter. Okay, I drank alcohol at this time. So 3 minutes later, the current is increasing rapidly, like this one. And then decreasing like this one. So this is a real-time detection of alcohol gas from my skin. So as a conclusion, we developed the ultra-sensitive alcohol skin gas sensor based on enzyme reaction by using a cellulose nanofiber framework electrode. The detection range is very enough to detect the skin gas of ethanol skin gas. So finally, I would like to thank you very much, this company and the university, also research funding. Okay, thank you very much for your kind attention. Terima kasih.
Thank you very much, Professor Tominaga. It is very nice talk. So we now move to a discussion session. So I will open probably two questions for the floor. Okay, Bu Yunita, please.
Sorry, I could not listen well. The voice is small.
Hello, can you hear
Hello?
my voice?
Yes. Yes. Okay. Okay. Yes.
Okay. Thank you. Ohayo gozaimasu.
Ohayo gozaimasu.
Genki desu ka?
Hi. Thank you very much for your inviting me this.
I should say thank
Okay,
you
go
for
on.
you because this is a very nice topic. This is new for me. I'm interested in a skin gas sensor. Because before my research in Enaga Sensei laboratory is about gas, but we detect this gas sensor. You use the enzyme modification, right?
Right, right.
Yes. As we know that the enzyme have short life.
That's right.
Yes, and then also in some enzyme just live in the specific temperature.
Right, that's
Yes.
right.
How you control the enzyme modified on the electrode? This
Okay.
is my questions.
Yes,
only.
that's,
Okay.
thank you very much. That
Thank you
is
very
very
much.
important question. Yes, so now mobile type glucose sensor is very, major, right? Everybody used. Also, the sensor use enzyme, right? And then also the electrode is disposable. So because the enzyme is not stable and maybe cannot store a long time. So the market is become larger. So I want to develop like this sensor. So yes, sensor is enzyme is very weak, right? But we can change the disposable electrode every day. So we can maybe we do not need care about the stability of enzyme when we use when we change electrode every day. Also, company is happy. Right.
So this is possible, right? So every
Right,
day we
right.
can throw.
Yes, that's right.
It is interesting because the selectivity must
Yes.
be excellent because the
Yes.
enzyme is only detect the
That's right.
ethanol. Then yes.
Yeah.
But just I worry if it is not stable or if the human error when we use, then it is some error. But it's good idea.
Yes.
I like that.
I think the selectivity is very important, right?
Yes.
Yes. So enzyme has very nice selectivity. Yeah.
Okay, Sensei, that's all of my question. Thank you very much. I
Thank you very
satisfied your answer. Thank you.
Okay, thank you, Bu Nita. The second question probably Najwa Nabila. Please.
Yes, thank you for your time. Before, let me introduce myself. My name is Najwa Nabila. Watashi wa namae wa Najwa Nabila desu. Kalimantan kokodai kako kara. Sorry for turning off my camera and my question. Watashi no setsuman wa, we already know a lot of company using some kind of smartwatch or a smartband are having some kind of metal tin in the back of the smartwatch and the smartband. But I already saw in the slide about the metal tin or the metal material to detect it, the health monitoring. So my question is, what kind of feature that Masato Tominaga-san making some kind of an updated another side of health monitoring? Like there's a lot of thing in the company using the health monitoring system in their smartwatch and smartband. And do you have another innovation to make another feature besides that health monitoring system on the smartwatch and the smartband? Thank you. Arigatou gozaimasu.
Hi, arigatou gozaimasu. Thank you very much for your question. Yes, in our system, if we change the enzyme, we can detect another gas, right? So also now we prepare the big size of electrode. Size is 5 millimeter, 15 millimeter size. But when company, company can make a very small size of electrode. I think maybe 3 by 3 millimeter is possible. And then also we can collect some sensor. For example, ethanol gas sensor, aldehyde gas sensor as sensor, right? We can collect the 4 sensors in the one chip. Maybe the total final size is maybe 5 by 5 millimeter. It is possible. Also, we use the potential stat and we observe the current. That is very simple mechanism, very simple detection method. So we now I use very large, electrochemical analyzer, but the company can make a device inside the smartwatch. So backside of, for example, so this is a smartwatch. In here we can set the our electrode, disposable electrode. I change every day, and then automatically detect the skin gas. So in here, I think like this future is realized in your future. My answer is okay for you.
はい、わかりました。ありがとうございます。富永正人さん。
Okay, thank you very much, Najwa. I think we have no time anymore, so we can conclude the session from Professor Tominaga. So thank you very much, Professor Tominaga. It is a great talk for you and from you, and it's great topic as well. So let's give a big round of applause for Professor Tominaga.
Thank you very much.
Okay, thank you very much. We move now to the next session and next talk from Professor Zaini Haryati from University Teknologi Mara. She will talk about the past, present, and the future of electrochemical sensor. So, but before that, I will briefly introduce Professor Zaini Haryati. Professor Zaini Haryati is currently a professor at Department of School of Chemistry and Environment, Faculty of Applied Science at University Teknologi Mara. She got her bachelor degree in industrial chemistry, and then she continued got master degree MSc in analytical chemistry with the thesis chloroquine sensor coupled flow injection analysis. After that, Professor Zaini Haryati obtained her PhD degree in electroanalytical chemistry by developing implantable deserine micro biosensor. Professor Zaini Haryati has published numbers of publication from 2017 to 2022 at the moment, and in peer-reviewed journal as well as in the peer-review conference. So, Professor Zaini Haryati, the time is yours.
Assalamualaikum, very good morning. Can you hear me?
Yes.
Good morning, everyone. Thank you, Dr. Izil, Dr. Yunita, Tominaga-san, Inaga-san from Japan, Professor Nurul Widyasuti, the President of ITK. Thank you for inviting me to be to share a bit on my work in my lab. I'm from University Teknologi Mara. I'm heading the Electrochemical Material and Sensor Group, in short, MAS. I'm also now the Deputy Director of Research Nexus in Energy and Environment Group. All the research about energy and environment, I manage them in UiTM Malaysia. From the UiTM is located near Kuala Lumpur, 20 minutes from Kuala Lumpur Airport, KLIA Sepang. And this is the largest university in Malaysia, and we are located in all the states in Malaysia. We have 14 branches all from Malaysia, and we have 8,444 academicians or lecturers, and almost 100,000 students all around the country. You can find more about UITM, and now we are aiming to be on the world map. Hope to be in Balikpapan soon. So I hope that Dr. Idil, we can work together in exploring more on electrochemical sensors and material. What is electrochemical sensors? They are devices that provide real-time information. It can be quantitative or qualitative. So basically for sensors, some journals like Biosensors and Bioelectronics, Electrochem, ACTA, so they are more on analytical devices. So you have to have your sensors to be characterized analytically, meaning your calibration curve, your RST percent, your reproducibility, reliability, shelf life, and everything. So that is more on sensors. But some of our colleagues also do on detection only, that is qualitative detection. So they can publish in a low rank on their work. So it's a real-time information. It can be qualitative and quantitative about the composition or whatever target molecule that you want to detect. Okay, using a very selective recognition element of your choice, like Professor Pamindaga just now. He used nanofiber from natural resources. That's great. Okay, and we can also use nanoparticles, materials like graphene. Prof. Iginawa use diamond, boron dope diamond, and as for myself, I'm more into screen printed electrodes, carbon electrodes. Then we modify the carbon electrodes with nanoparticles. So why electrochemical sensor? Because they use electron for signal acquisition. So electrons, most of the participants here maybe are undergraduates or postgraduate Dr. Idil. So I hope they know what electrons is. So electrochemical sensor, we can detect that signal produced by the electron transferred or electron changes, okay, on the electrode surface. So this technology is considered clean, green technology for analysis because there's no waste, reagentless. It can be miniatured into very small device, a very small, tiny samples volume that we need, fast analysis, low production cost, and we are going towards the net zero transitional process, decarbonization of things. So electrochemical sensor is the future for what you call that, for the future technology. Okay, so furthermore, electrochemical sensors were found in very wide range of commercial application, just like our previous speakers mentioned on environment, in detection, in healthcare, and many more. Okay, basically it's come from this equation, the electrical signal produced and the E naught, the energy, every molecules that have electrons, okay, moving around them with the pi bond of the bonding in the molecule. So if there's a free electron, we can use that properties to activate whatever redox or oxidation reduction process, transferring the electrons from one compound into another. So transferring the electron, every molecules or every substance, okay, with electron, they have their own internal energy, the delta G, delta Gibbs. So delta G also relates with the E, electrical energy. So from this equation, all electrochemists can work on sensors. Further on, if you want to do the analysis of electrochemical analysis, this is the equation. The Rayleigh equation that relates the currents with the number of electrons, electron area, diffusion coefficient, scan rate, and also the concentration of your target analyte. So it goes to the tool that is cyclic photometry, or electrochemist known as the dark shape voltammogram. Okay. So from here we can know whether the process are absorption process, diffusion process, how many electrons involved, what are the concentration of your target, and then write the lowest that you can detect is the best limit of detection. The principle of electrochemical sensors are based on the use of redox hypothesis. It can be your reduction or oxidation process. So the hypothesis that we couple in our architecture in designing the sensors that is born into the biomolecules or whatever molecules that you want to attach the redox hypothesis. Some the community call this ionophores. Okay, electron capture material. Okay, so the material can bind or react with our target analyte, and whatever electron transfer happen between this reaction can be captured on the electrode surface. Okay, so when we are talking about electrode, you know the principle of this V equals to IR. We can capture the current, the voltage, or the resistance, or now we are going to the impedance detection, EIS. So these are the examples that I've done on electrochemical sensors. First, detection of gunshot residues in forensic application. So we tested different firearms and different ammunition. So from this study, we can identify, because from the work, the detection, we have to like make some deep learning and chemometric analysis. And from the data, we can identify which firearms that is being used from the detection of the gunshot residues. Okay, so this is on-site sampling. So we use the screen printed electrode after the shooting, and then we run the CV. Okay, from there we get the signals of the metals in the GSR and also the organic compound in GSR. And then well separated peaks found, then we can identify which peaks or which signal relate to the firearms and the ammunition. Another example is, the trace determination of cadmium in Malaysian herbs product using graphene and ionic liquid. We use ionic liquid because as Professor Inagasan mentioned just now, because of the wide separation electrochemical window. So using ionic liquid can solve the problem of peak separation. Okay. This is another work, detection of nicotine, the tobacco compound, okay, in e-cigarette on nano gold modified screen printed carbon electrode. So we found there's a unique peak produced by nicotine as compared to other materials that in the e-cigarette, what do you call that? E-cigarette liquid, okay? So then we can quantify the amount of nicotine in e-cigarette, because more, I mean, the assess limit of nicotine will become harmful to our health. Okay, so using the what we call gold nanoparticles that we deposited on the screen printed carbon electrode, it produced a greater signal. This is on ferrocyanide. Okay, as compared to the commercially available screen printed gold electrode and screen printed carbon electrode. So our modification enhance the signal of the commercial electrodes. So for environmental analysis, so electrochemical sensor can be used in very wide detection in heavy metals, in pesticides detection, nitroaromatics, and also emerging pollutants, based on the principle of the oxidation or reduction of this compound on your electrode. So how to increase the signal is where you have to modify your electrode, or you use a specific recognition element to enhance your sensitivity and selectivity towards the target of your sensors. Another application is on health care. Also in Malaysia, there's a mortality rate that is listed. The current major diseases in Malaysia, there are two types of diseases: communicable diseases and non-communicable diseases. So the first, of course, our what the most popular diseases ended, the pandemic ended this year is COVID-19, and for non-communicable diseases, the top in the list is cancer. So I have what experience on doing these two types of sensor for these two diseases. Okay, so yes, from healthcare is the way forward. I think that for all the electrochemists on sensor have to go to survive or to sustain our research into. Okay, so we go into the healthcare. So we're dealing with bioanalysis. Bioanalysis is defined as quantitative. Bioanalysis must be quantitative. It can be also qualitative, but if you want to go for qualitative, you have to have a reference standard, you have to compare your detection with the gold standard, whatever your Ministry of Health, the regulation in your country, okay, to validate your sensor. Measurement of analytes in biological matrices. It can be body tissue, blood, serum, urine, and any other related to human. So medical definition, the identification or measurement of substances such as drugs, metabolites, proteins in a biological system, such as this biological system in human. Okay, so there's lots of biomarkers in biofluids. This is not this is only an example, but it's like unlimited amount. We can venture into many more. Okay, if you read the literature, there's a humongous amount that you can explore into. So when dealing with biological target molecule, we cannot run from the electrochemical biosensor, where we use bioreceptors as the sensing element, the sensing material. So the bioreceptors, like the previous speakers have mentioned, we use enzyme, or now enzyme has been replaced by aptamers because aptamers are more stable. Okay, microorganism, we use the real whole cell of the diseases, DNA and everything. So that's where we go into biosensors, electrochemical biosensors, because biosensors, they have optical, they have mechanical, they have also now electrochemical. So we focus on electrochemical biosensors. Okay. So speaking of which, diseases are around us. It can be like aging population is coming up, and the what you call it, the management, the treatment of the disease must be fast, okay, on time. And the problems are the high or expensive cost of getting very high-end instruments to detect the diseases. We need like a very simple portable like glucose detection here. Okay, this is also the concept of potentiostat and glucose detection is on enzyme. Okay, the glucose oxidase here. So there are lots of illness, okay, that have biomarkers with that. So it's on us, the electrochemist creativity, to be able to zoom or to detect all these diseases. And the latest is the COVID-19. Okay, it's very harmful to put the swab into the children. Okay, they are very painful for them. So here it comes to the sense and sensibility of electrochemical sensor, because electrochemical sensor provides a point of care testing. So during the consultation, the doctors can give a very fast results, leading to an immediate and informed decision about patient care. Okay, so electrochemical sensors be able to provide specific answers to specific analytical issues, like the amount of glucose in your blood, the amount of cortisol for stress, okay, amount of you name it, whatever hormones, okay, that relates to the diseases. So these are the WHO guidelines for diagnostics of in resource limiting settings in Malaysia. We have lots of rural areas still underdeveloped in terms of a very high-end equipment. Like we in Kuala Lumpur is a modern community as compared to over in Gua Musang, Kelantan, for example. So people from rural areas have to travel very far to the hospital and to get appointment like 6 months before to be diagnosed of diseases. So for a very resource limited setting, the device must be affordable, sensitive, specific, user-friendly, rapid and robust, equipment-free, and it can be delivered to those who need it. That especially for our communities in rural areas. So this is the what they call that opportunity for electrochemists to venture into electrochemical sensors for healthcare monitoring. There are lots of current diagnostic techniques: ELISA, PCR, microbiology culture, chromatography, and you name it. Okay, this is all very lab-centered, very skilled personnel must can run. Only person with that skill can run these tests. Okay. And it's time-consuming, a very complex and expensive instrumentation. So you have a wet lab far away from the villages. So waiting time for the diagnosis can be hours to several days. So late therapy administration, major problem in emergencies, inefficient population screening for like us in Malaysia, in rural areas. So we need electrochemical sensors here, especially electrochemical biosensors that can provide the possibility to create miniaturized point of care devices containing the functionalities of an analytical laboratory, meaning that when we develop the sensors, it must be to the standard of whatever the Ministry of Health or WHO has been using. So currently, this is our work on COVID-19 detection. From the virus, we have to select what is the best biomarker for the real-time monitoring, acute monitoring, meaning that when you hit by the virus at that time, what is the element that we can detect? We are focused on the RNA, and then we extract the RNA and then study the bioinformatics, and we determine the dominant region of the what do you call that, the virus. So we have E gene, N gene, RDRP gene. So within that genes, we identify the dominant regions and we take out that region to be the biorecognition element for our sensor. And from the extraction, we use the amplification method to amplify the DNA from the virus, and then we drop it on the screen-printed electrode and detect it using the differential pulse photometry. The carbon screen-printed electrode must be modified with the nanoparticle to enhance the electron signal, the electrochemical signal produced. So for brain, I mean the neurochemicals detection in our lab, why we are interested in NCF, neurochemical fluid, because this brain have neurochemicals. Okay, the neurochemicals without we knowing, okay, is controlling our body. The beating of our heart, the rhythmic beating, it is being controlled with certain neurochemicals. The learning process, the socializing process also depends on the neurochemicals, and handling of our emotion, okay, also relate with the neurochemicals. So here the electrodes can be used to analyze the neurochemicals in brain. So the direct measurement is important to be used for the neuroscientists in the drug development phase, okay, to answer important questions on timing, dynamics, quantity, and location of neurochemicals in brain, that they can understand more about the brain functionality in human. So furthermore, in vivo detection using microbiosensors have been developed, and it is possible to investigate the systemic administration of neurochemicals in several brain areas. like our team has done on the dopamine effect of increment during the administration of a kratom compound. Okay. So previously or memang conventionally the brain analysis we use microdialysis, but the probe is too big and it's an ex situ analysis that cause significant damage to brain tissue with poor temporal resolution. That's around 10 minutes. But for implanted amperometric electrodes, very small, the diameter, internal diameter is 50 micrometer, and it provides signals within seconds. So we developed the in vivo monitoring of glycerin, glutamate, acetylcholine, dopamine in brain in a live animal, what do you call that? Yes, it's crucial, but for science, this is with ethical approval. Okay. So for glycerin, we use enzymatic conceptual. For dopamine, we use a non-enzymatic. I think Professor Tominaga have mentioned just now on the enzymatic electrochemical sensors principle. So I have to. So the steps are you have to do the calibration curve and cut the Nicholas-Menten and everything. And then you determine your sensitivity, your reproducibility and everything, okay, to make sure that the electrodes works well. And then the characterization of your the electrode surface and everything, and the selectivity study and the application of your electrodes in real-time monitoring of the animal. Okay, so our recent work has been published in Neuroscience Letters last year, and this is work on real-time monitoring of dopamine release evoked by mitragynine, a compound in kratom, using electrochemical sensor. Okay, we found that this compound mitragynine in kratom is a plant in Malaysia that people drink for being active to get being alert like a coffee. Okay. Then this compound exposure to the mitragynine motivate dopamine release, and the monitoring was done. We implant the electrode and we measure the dopamine release using this platinum modified with polyphenol diamine polymer electrode, platinum electrode, or in the brain. Why we use PPD? I think this is for another session. Okay, we also developed the Alzheimer disease immune sensor. Alzheimer, we are targeting alpha beta 40 protein using a very specific antibody to detect this antigen, and we use EIS impedance. Why we use EIS? Because it is labelless without label, and it can produce without potential. We don't give potential to the electrode, so they will not burn the brain cell. Okay, so impedance is better than the voltammetric technique. So these are the formula and calculation for determine the affinity of amyloid beta protein with our antibody. Okay, when it's more towards 1, so it's good. So then you can use your electrodes. Okay, with this sensitivity, and we have to compare with the standard method. So here in Malaysia, they use ELISA for alpha beta 40 detection. So whatever sensor work, if you want to publish in a very high, what you call it, journal, impact journal, so you have to compare and validate your results with the current method of detection. Okay, next is the circulating tumor cells, that is cancer. Approximately 1 circulating tumor cell per billion of other healthy blood cell is in our circulating system. So 1 ppb per billion. Okay, so if we have work on ppm, next the next is ppb. So if we can go lower, so the detection of CTCs is possible. I call it. I have to emphasize that it's possible, meaning that you are able to design a very good sensor architecture with nanoparticles, with good transducers, and biorecognition element. Okay, so this is also the future for electrochemical sensor is for cancer detection. Okay, in from Globacon, the statistics that because I'm focusing on breast cancer, this is the statistic for the breast cancer cases in Malaysia in 2018. In Malaysia, we have 7,500 cases. You look at the number in Indonesia and Japan. So let's work together and do this seriously for breast cancer detection. Tommy Nagasan and Dr. Aidil, okay? We can collaborate on working on breast cancer detection, inshallah. The mission is to build a breast cancer screening device prototype that relates to early detection, faster and accessible. So if we are able to detect the biomarker for breast cancer, we can we call that. If you can detect it early, it's curable. If it can be detected at early stage.
Sorry, Dr. Zaini, you have 5 more minutes.
Okay, based on the secreting at CTC just now. As compared to the current diagnosis, it's very painful and we have to withdraw the tissue from the patient and everything. So, and the equipment is expensive. So for electrochemical sensor, it's based on the single-stranded DNA as the biological recognition element. So before we doing this, we have to study the bioinformatics and design our specific sequence. And these are the electrochemical techniques that you can use for detection. We are using EIS, okay, and also standard method DPV or square wave voltammetry. And also we attach to them zinc oxide nanowires to hold this single-stranded DNA for stability of our biorecognition elements. So for currently, they are using PCR and NGS in the lab. So these instruments are expensive. So why not we use a sensor that can eliminate the analysis time, reduce it into 98% faster, and very small number of blood volume. Okay, so the sensitivity and the specificity is very good, but our study is only on MCF7 cells. We extract the DNA from MCF7 cells. So these are the commercial electrochemical nucleic acid detection system. So in future, maybe our colleagues here can design a more portable device, okay, a small device compared to all these bulky instruments. So the future now we are venture into the internets of personalized medicines of things. So we are attaching the sensors with the cloud and the what do you call that? AI, artificial intelligence, okay, deep learning. So that's the we have to go to the electrochemical sensors and AI. So there's lots of examples in literature. So I would like to invite all of you researchers that are interested to do work we can do together to venture into the futures of electrochemical sciences. So the target desirable requirement for future electrochemical sensors in healthcare, it must be point of care, it must be wearable, or you can like attach your sensors on the organ on chips, okay? So all these characteristics for sensing features must be sensitive, must be long-term use. So sorry, Tommy Nagasan, maybe the enzyme you have to like turn it into Actimus for long-term use. The material must be non-expensive, disposable, biocompatible, and flexible because we are putting it on skin like Tommy Nagasan shared with just now. The nitrocellulose film that you shown is very great example for great flexibility. For fabrication, mass fabrication, high throughput, low cost, and maybe with microfluidics, coupled with microfluidic because lots of biochemical reaction happening there. So microfluidic maybe we can add in our into the sensor or device. And for deployment, it must be portable and wireless. This is where IoT, Internet of Things, come in. Okay. So for future, bear in mind that we have to think about the sensor architecture, sensor material, sensor usability and feasibility. Do not compromise with the sensitivity, selectivity, speed, and of course, it might be safe for the end user. That is about all. I have to acknowledge all my students, my colleagues in our team, and all the grant providers that have funded our research project. Thank you very much, and please come to meet us or discuss on to working for the future electrochemical sensors. Thank you.
Thank you very much, Professor Zaini. So we now go to discussion session, but before that, I will remind to all participants to fill the attendance list as mentioned in the chat room. So, okay, I will now open 2 questions probably to the participants to give a question. Please. Who wants to give question? Does anybody?
I would like to ask question. This is a very interesting topic. To Dr. Zaini. Assalamualaikum. Yeah, I'm interested in breast cancer detection. What is the working electrode to do that, and how? Or we take the sample from the body and then we detect, or how? Because in the medical application, electrochemical sensors now is a very booming, popular. So I would like to know the mechanism. Thank you very much.
Thank you for the question, Dr. Junita. It is the principle is the biosensors, electrochemical biosensors, because the breast cancer is our biofluid, the samples. Okay, so we determine the biomarkers for the breast cancer. Okay, we are focusing on the cancer cells, MCF7 cancer cells. So we extract the DNA from the cancer cells, and then we do the bioinformatics and find the dominant regions, and then we design the aptamers for the DNA, breast cancer DNA for MCF7 cells. But MCF7 cells, there is in breast cancer. For other cancers, they also have specific cells expressed from the cancers. Okay, so maybe we can talk. We can discuss further more on this. Maybe you can contact me through email or through WhatsApp.
Okay, Dr. Zaini, I get it. Thank you very much.
Thank you.
Okay, thank you, Bu Nita. Professor Tominaga, please.
I have one question. Thank you very much for your very interesting talk. My question is about the dopamine sensor.
Sensei, your voice is very small.
I cannot hear your voice, Professor Tominaga.
Okay, thank you very much for your nice talk.
Welcome.
Can you listen my voice? Okay. Can you listen my voice?
It's very far.
Yeah,
not
it's very
clear,
far.
I'm so sorry.
Okay.
My question is about dopamine sensor.
Yes.
Yes. So I think you use the platinum covered with some polymer, right?
Yes.
So what kind of polymer did you use? And what is the role of the polymer?
Thank you, Professor Tominaga-san, for the questions. We are detecting dopamine in real time where we implant this microsensor in the brain. Okay, so we use platinum microelectrode. Okay, where we put the platinum bare without the polymer. So in the brain, we have ascorbic acid, we have hydrogen peroxide, we have a lot of other neurochemicals that can be reduced or oxidized. So polyphenyldiamine, PPD, polyphenyldiamine, the polymer, the conducting polymer is being electropolymerized on the platinum surface. So it is a film, the PPD film, to reject a very big molecules like ascorbic acid to diffuse into the platinum electrode surface. So we can be selective towards dopamine.
I see, understand. Thank you very much.
Thank you, Namiga-san.
Thank you very much, Professor Taminaga. I think we have no more time. So with that, we conclude the session from Professor Zaini
Thank you, Dr. Idil. Assalamualaikum.
Those who want to contact again may contact.
Yes, my email is there on the screen.
Okay. So thank you very much, Professor Zaini Haryati. So with that, I conclude this presentation session, and I will turn back the time to MC. Thank you very much.
So thank you so much. Oops. Thank you, Dr. Andi. Thank you for the insightful speech from the speakers and lively discussion from the participants. Thank you also, I have to say, to our moderator, we are very proud of Dr. Andi Idil Ismail for leading the session amazingly. Before we move to the main agenda, I would like to introduce you all to our management who support this world-class professor. There he is. First is Ibu Umi Sholika, the head of Environmental and Earth Science Department. Hello, Ibu Umi. Okay, next is Bapak Jatmoko Awali. He is the head of Materials and Metallurgical Engineering undergraduate program. Hello. Okay, and then me, also as a secretary of the Environmental and Earth Science Department under Ibu Umi Sholika. And then also there is Dr. Muhammad Purwanto. He is the head of Research and Community Services Center in ITK.
Assalamualaikum.
Waalaikumsalam warahmatullahi
Thank you.
Thank you so much. How are you?
Alhamdulillah, I'm fine.
Alhamdulillah, you're fine. Okay. So in the Research and Community Services, there is a integrated laboratory also. So the MOU later will be a cooperation between integrated laboratory ITK with KU University. And then next, the last but not least, the beautiful one, Dr. Musyarofa. She is the head of international office. Hello, Ibu Ova.
Hello, good morning, everyone.
Good morning. Thank you. Thank you so much for participating.
So sorry, Mrs. Lala.
Yes.
Einaga Sensei, can you on cam your camera? We would like to spotlight.
Please, Einaga Sensei.
Are you there? Okay. Okay, Sensei, thank you very much.
Thank you very much, Sensei. And this is our management who support us in the world-class professor and also the MOU with you later. Thank you so much for participating with us today. Okay, we are arriving in the final moment right now, a legal signing ceremony between the Integrated Laboratory of ITK and the Diamond Electrochemistry Laboratory, KU University. For your information, ITK have already had international collaboration with Saga University. Thank you for Tominaga Sensei who put trust on us. I thought maintaining relationship with us is not easy, but he is very kind to support our programs like webinar, guest lecture, and will be the plenary speaker in our international conference in October 26 in this year. And addition, Sensei always give us opportunity to join the Sakura Science program with him. Gladly, after pandemic, we could send our staff and students to Saga, Japan in the end of this year. Thank you so much, Sensei. We appreciate your hard work. And recently, we also have an international collaboration with University Teknologi Mara Shah Alam, Malaysia, or UITM. Thank you for Dr. Zaini Haryati to permit our students to conduct research in your laboratory. I hope that we can produce many impactful journals from our joint research in the future. And I hope also it's not only our student is being delivered there, but also your student can come to ITK doing research, attending class, or cross-cultural study, maybe someday, hopefully. And now we are having one more international collaboration with the Diamond Electrochemistry Laboratory, Keio University, to strengthen and improve our education and research quality. Thanks to Einaga Sensei, we are extremely joyful for having you as a partner of ITK. Together, we enjoy the video. Okay, thank you so much. That's so wonderful. And now we together listen to the short speech from the head of Research and Community Service Center of ITK, Dr. Muhammad Purwanto. Time is yours.
Hey, thank you, Miss Gusti Umrian Nur Tajalla.
Yes, sir.
The famous nickname is Mbak Lala. Okay, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon and greetings. Respectable Director of Institut Teknologi Kalimantan, Profesor Budi Santosa, Excellencies, the Vice Rector of Academic Affairs, Institut Teknologi Kalimantan, Profesor Nurul Widastuti, Excellencies, the Chairman of Multiple Professor Program ITK, Mbak Yunita Triana, PhD, Excellencies, Dr. Musharofah from International Office, Mbak Umi Solihah, STMT from Department of Earth and Environmental Science, Jatmoko and all honorable speakers, Professor Dr. Yasuaki Enaga, thank you, Prof, from Keio University, Japan. Professor Masato Tominaga from Saka University, Japan. Nice to meet you again, Prof. Thank you. Associate Professor Dr. Zaini Haryati from UITM, Malaysia. Thank you, Prof. And all researchers and colleagues and students from various institutions. Ladies and gentlemen, thank you to each and every one of you for being here today at this wonderful opportunity in the virtual meeting, the world-class professor meeting series. My name is Muhammad Purwanto from Research Institute and Community Service that coordinate all research activities and facilities in the integrated laboratory. We are very happy and thank you very much for Professor Yasuaki Enaga, Head of Diamond Electrochemistry from Keio University. Thank you very much, Prof, who is willing to collaborate with the integrated laboratory Institut Teknologi Kalimantan. We hope that this agreement will lead to many research collaboration, joint publication, or student agents, and more. Just for your information, it is the Teknologi Kalimantan today, 6 October, is ceremony of ITK anniversary that was found in 2014. I think this is an opportunity for us to build a strategy for research development in the future. So this agreement can be followed up in the future through a memorandum of understanding or MOU between Institut Teknologi Kalimantan and Keio University. Okay, I think it's enough, and thank you for your attention. Greeting Hadley. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Dr. Muhammad Purwanto. Excellent speech. And then the last but not least, Einaga Sensei, I give you an opportunity to give a short speech after signing legal ceremony. Einaga Sensei, time is yours.
Okay. Thank you very much. I wanted to thank you, all of you, especially Dr. Yunita Triana-san, for not only her, but everybody. I want to thank you for this very hard job to set up this program. I think this is very troublesome to prepare from the beginning. Anyway, thanks to all of your effort, we could have an agreement for the collaboration. I'm very happy for that. Actually, so far in my group in Keio University, I accept many Indonesian students, especially from University of Indonesia, especially. But all of the Indonesian students are very, very active and very, very working hard. So I'm so impressed with this hard working and getting a good result anyway. So that's I'm very expecting. So actually, this is the first time to accept a student from ITK. This is Nita-san as a student this is the first time for me, but from now, this relationship between Keio and ITK will be increasing. This is a very good opportunity, and I'm very expecting the not only good result, but Japanese students also get some encouragement from the students from Indonesia. So that's also a good point. So anyway, I hope our collaboration will going well from now. So today, actually, this is a internet meeting, but later, of course, in person, please, we also want to visit there, and please come here. This is a more important to communicate in the near future. Almost corona situation is not perfectly recovered, but the situation becoming normal gradually. So from now, I'm also expecting such a collaboration and interaction. Anyway, thank you very much again.
Thank you so much, Enaga Sensei. We hope in the next future we have a larger collaboration, not only with your laboratory, but also in KU after all. And thank you. For the participants, I would remind you to fill out the attendance form in the chat box. And this is some kind of placard and certificates of appreciation for the speakers of today. Please, committee. The last but not least, thank you for all the participants who come to the world-class professor, because all of you, the webinar is successfully conducted. The participants is always more than 100 coming from, it is not only from ITK, but also experts in electrochemistry, especially in boron doped diamond sensor. The first theme, strategy of preparing research management group and writing proposal to reach international grant with 393 participants. And the second theme, promising materials and boron doped diamond electrodes for the electrochemical sensors with 240 participants. And the last theme, existing and future perspective of electrochemical sensor with 136 participants. We appreciate your enthusiasm, and do not forget to fill out the attendance that our committee provide in the chat box to get an e-certificate. Finally, we are in the end of the webinar. Hopefully this event could give you fruitful inspiration. We apologize if there are any mistakes from the committee. Hope you have a great day. See you in the next webinar. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you, Enaga Sensei. Thank you,
Thank you, Prof.
Thank you so much. Pak Put, terima kasih.
Terima kasih, ternyata luar biasa. Jos, mantap.
Bumi, makasih Pak Jat, makasih Bu Lala, Bu Ova.
Ya, terima kasih Bu Yunita.
Welcome to Material and Metallurgical Engineering ITK. I'm Jatmoko Awali, the head of department. I know there must be a lot of questions about what we can do on this study program. Let me get you to take a look at the journey that you can choose to assess your universe. Our strategy to solve these various problems is by dividing our expertise in four broad research areas: material simulation and modeling, material manufacture, innovative material, material viral analysis. Let's find out what they are doing.
Material simulation and modeling expertise cover research for modeling and simulating important aspects in material science, including structure, properties, and behavior of materials. Basically, we are trying to construct models and identifying the correct approaches to test theoretical descriptions, experimental observations, or non-experimentable materials phenomena using various computer softwares.
Materials manufacturing studies the processing of materials to improve the efficiency and effectivity of product manufacturing. For example, casting, soldering, carburizing, welding, sintering, polymer extrusion, and composite curing.
Innovative materials focuses to improve materials by curating and developing innovative composite, metal, polymer, and ceramic, by expanding the design for devices and systems of technological applications such as industrial, medical, and environment.
Material failure can lead to catastrophic accidents like the Titanic, airplane crashes, or collapsing bridges around the globe. The program teaches the student to analyze cracks, corrosion, deformation, and many forms of material failure to find the causes and design the prevention of material failure.
So, that is a glimpse of the universe that you can choose. Let's start your journey with us to see more and know more. Because
there is no engineering without materials.
There is no engineering without materials.